At no point in your rambling, incoherent response were you even close to anything that could be considered a rational thought. Everyone in this room is now dumber for having listened to it.
You lose! Good day!
Hi, welcome to CheMistakes. Here we go through actual student responses to questions and try and learn some things from them. Here we have a challenging acid-base question about pH upon the mixing of a strong base and a weak acid. Student answer is here. They had an equilibrium constant given to them, set up an equilibrium expression, plugged in X for both of these concentrations, divided by 0.1, the initial concentration of this, solved for a value of X, took the negative log, and got a pH of 2.2. So there's a lot of errors going on here, and there's a lot of things that are lacking from understanding potentially from the student. So I want to go through all of those different features, but basically we want to kind of set up some fixes. So when you're doing an acid-base question, it's really important that you have a good understanding, first of all, of what are all of the different styles of acid-base reactions, and really being able to separate between those reactions, which of them are stoichiometry-based and which of them are equilibrium-based. Okay, and then at the end of this, we want to come back and revisit what are some of the common errors that will happen in questions like this that we want to avoid at the end when we go back to look at it. Let's start though with stoichiometry and equilibrium and acid-base reactions. So when you're doing a pH calculation, somewhere along the way, there has to be an involvement of water. And so in this particular case, the things that we're starting with is we're starting with sodium hydroxide, and we have a weak acid, hydrofluoric acid. Right. So when you're dealing with anything strong, that reaction is going to go to completion. A strong base is good at removing an H+. It will remove every single H+ from that acid. Even though this acid is weak, the combination with a strong base means that that reaction is going to go to completion. So you'll often see neutralization reactions like this, drawn with a single arrow like this, indicating that it's going to react completely. So we're going to end up forming sodium chloride and water. So for this, we're doing a stoichiometry calculation. We need to know how many moles of each chemical we have, and then we can figure out what we'll have in the end. Now to figure out moles, many students are not very keen on this, but the volume and the concentration combine to tell you the moles. So molarity is moles per liter, or moles per decimeter cubed. And so the molarity times the liters will tell you the moles. So we'll write this often as molarity times volume. So in this case, I have 0.1 molar times 0.01 liters, okay, because 10 milliliters is 0.01 liters. So when I multiply those, I get 0.001 moles. So the number of moles of sodium hydroxide I have initially is 0.001. Let's call that before the reaction takes place. Then I mix it with 10 milliliters of 0.1 molar hydrofluoric acid. That's going to be the same calculation. So I also have 0.001 moles of hydrofluoric acid. Okay, let's assume I start with 0 of this, and we don't really worry about the water in this particular case. So then when these react, these are going to react completely. Now there's the same moles, and they react in a 1-to-1 mole ratio. So this is going to completely react. This is going to completely react. I'm going to end up making 0.001 of this, and I'm going to add 0.001 moles of whatever original amount of water I started with. So when I'm done after the reaction, after it's changed, I will have 0 of my reactants, and I will have 0.001 moles of sodium fluoride. Okay, and then I'll have some water present. So when I go back now, it says find the pH of this. Well, now I'm looking at this chemical being present and somehow reacting with the water. So what is this chemical? Well, what we have here is we have a weak acid, hydrofluoric acid, and we have the fluoride here, which is the conjugate base of that. And so we have a base reacting with the water. We have 0.001 moles of it. So we now need to kind of do a new equation that's not a stoichiometry equation. Now we're going to look at a weak base plus water. Now before we do that, let's take this final answer and change it into concentration. So at this point, we now have 10 milliliters plus 10 milliliters. We have 20 milliliters total, which is 0.02 liters. So our concentration of fluoride is going to be equal to 0.001 moles divided by 0.02 liters, which is going to be 0.05 molar. Okay, so half of our original concentration. All right, so let's go ahead and delete this. Our now look at a new equation. So now we're looking at fluoride reacting with the water. Remember, we only had fluoride present, that's the only thing that can react. This is a weak base in water. So whenever you have something weak in water, that's going to be an equilibrium setup. Now, what does a base do? It pulls an H plus away from something else. So that's going to produce a hydroxide from the water and the conjugate acid, hydrofluoric acid. So we're starting with 0.05 molar of this. Nobody cares about the water because we're looking at equilibrium and that's a liquid. And we're starting with 0 and 0 of this. Technically a really tiny negligible amount of that. So now we're doing equilibrium, we're now going to do what's called an ice chart. And the difference between a BCA table and an ice chart is that at equilibrium, you're not going to completely change all of those into these. You're not going to run out of something. You're going to have some of each thing present. And so now we don't say that we go down by 0.05, we're going to say we decrease by x. So at equilibrium, we'll have 0.05 molar minus some amount. Now the change is still limited by the stoichiometry here. So we're going to add x for this, some amount of this, some amount of this. Because every one of these that reacts with one of those will produce one of these and one of these. So if this decreases by some mystery amount, we know these will increase by that same mystery amount. So we end up with x and x. So now, when we look at our K expression here, we're looking at a KB expression for the base, and that's going to be equal to my product concentrations over my reactants. Keep in mind that water is a liquid is emitted from the reaction. So here I don't know my Kb, I know my Ka for hydrofluoric acid, I need to know my Kb for the conjugate base. So the Kb for the conjugate base is going to be equal to the Kw of water, 10 to the negative 14th, divided by that Ka. So in this case, my Kb is going to be 10 to the negative 14th, divided by 4 times 10 to the minus 4. Comes out to be 2.5 times 10 to the negative 11. So that is going to be equal to concentration of hydroxide, x, concentration of hydrofluoric acid, x, divided by 0.05 minus x. And we're going to simplify this down to simplify our math, just being 0.05. And our rationale there is that it's going to be such a small shift. We have such a small k value that we're not going to pull a lot. So we basically have 0.05 minus a really, really tiny amount. And so 0.05 minus that really, really tiny amount is still going to be about 0.05. We'll see that in a second. So we're going to solve for x here. 0.05 times our k value, and then square root it. Let's try that again. Calculator issues. So in this case, our x comes out to be 1.12 times 10 to the negative 6th. Okay? And if we take the negative logarithm of that, that's the negative log of x. Now x is our hydroxide concentration and our hydrofluoric. Well, the hydroxide concentration, if we take the negative log of that, that's POH. So now we have the negative log of that as our POH, which is 5.95. And our pH then is going to be 14 minus that POH, 5.95. So we're looking at 8.05. So our pH of this mixture is 8.05. Now, first of all, that's a pH that makes sense because we're dealing with the presence of a weak base in water. It's a really weak base because it's a really tiny K value, and it's not that concentrated, so that 8.05 would make sense in this context. If we go back now and look at what the student had taken a Ka expression and used that to plug in. They had done this ice chart process, but they had skipped it and just kind of gotten to the final result. And so because they didn't really fully apply this, and they didn't really go through and figure out what all these things are, there's a couple errors that we want to point out. One is because they did that, they left the concentration as 0.1 molar. And we saw here that our concentration was 0.05 molar because when we did the reaction, we ended up combining two volumes. And so we ended up dividing that by twice as much volume. We ended up with half the concentration. So there's a big error here. Obviously the K is incorrect because they're dealing with a situation where they're dealing with the product of this reaction and they're just looking at the K value and plugging that in. So what the student probably has learned here is they probably learned how to simplify down a calculation where they didn't really understand what was going on in terms of the reactions. And because of that, when they went to do the problem, they really only had this algorithm to kind of apply and they didn't really understand what they were doing. To fix that, you need to have two strong understandings. One is you want to be able to understand that some of your reactions are going to be an acid with a base, and that's probably going to be a neutralization where you go to completion and you're not doing equilibrium. Other problems where you have a weak base or a weak acid plus water is going to be an equilibrium setup, and that's where you're going to break out the ice chart and plug into the K expressions. This student started with a weak acid and a strong base, didn't identify that as this certain type of reaction with stoichiometry, went straight into equilibrium mode and misapplied the algorithm. Okay. The other thing is they missed the fact that they're dealing with a base and ended up with a pH of 2.2. So really what they did was they plugged in what would the pH be of 0.1 molar HF, ignoring this entire other component. And hopefully you get an idea of kind of how to avoid that in the future. So if we go back to like what our goals were, separating stoich from equilibrium is a theme that I really think is important. So we're looking at stoichiometry applications whenever we're dealing with a strong acid or a strong base in any context. Strong acid plus water, strong acid plus weak base, strong base plus weak acid, strong base plus water. All of those are going to involve a complete reaction, or complete enough that we can ignore the equilibrium components. For equilibrium, that means we're looking at a situation where we're looking at water. There are other contexts where you can have that, but really it's about having a weak acid or a weak base, or a weak acid and its conjugate base, or a weak base and its conjugate acid, with water. So when you have a situation like that, that's what you want to see. Now the weak acid and weak base, if we have a buffer, so if we had some HF and some F minus, those will then react with water, and we can set up an analysis there with equilibrium. Okay? When you have strong acid or strong base, you need to do a neutralization first, and then the products of that neutralization and the leftover reagents can then be analyzed from an equilibrium perspective. That feeds hand in hand to having a better understanding of acid-base reactions. Strong acid is so good at donating an H+, it has such a weak bond that that's going to go to completion. Strong base forms such a strong bond that that's going to go to completion. A weak acid is not as good at releasing an H+, and therefore that's going to set up an equilibrium where we have a back and forth. A weak base is not as good at removing an H+, it's going to set up an equilibrium. And then at the end, we want to watch for common errors. This was an error because they forgot to account for the dilution by mixing the two solutions together. The Ka versus Kb, here we've used Ka for a situation where we had a weak base present. And then always make sure that you put in that you're ignoring the minus x here so that it's clear to the person grading it that you've done that. And this one, if this had been the actual problem, they're getting close to that point where these are close enough that you're not actually having such a small change where you can ignore the minus x. So you definitely want to clue in the grader that that's what you're choosing to do in that particular instance to simplify down your math and avoid the quadratic, because of the convenience is worth the minimal gain of adding in that extra component.
Okay, a simple wrong would have done just fine, but